Okay, the next example we're going to do with the integral test actually is going to have a special name. We're going to be investigating the behavior of a specific series called the p-series. And the form of the p-series is a sum from n equals 1 to infinity of 1 over n, remember n is the index of our series, raised to some power p, hence the p-series. And for us, p is some number. And for example, what we want to know is, hey, right from the get-go, should we know if this series converges if, say, p is equal to 7, if p is 0, if p is negative 12? What values of p are going to make this series converge? And well, I just want to start off and give you the spoiler from the start. So if we have this series from n equals 1 to infinity of 1 over n to the power p. This series does two things. It converges when p is greater than 1, strictly greater than 1. And this series diverges for all other values. In other words, it diverges when p is less than or equal to 1. And what we're going to do in the rest of this video is really try to investigate why this happens. So, the first thing you might have seen is, or made the connection, we already know something about one particular value of when it diverges. Let's let the value of p equal 1. Oops. So the series that we're actually concerning ourselves with when p is equal to 1 is a series from n equals 1 to infinity of 1 over n. This had a special name. This is what we call the harmonic series. And we saw that this series diverged. Okay, well, let's see what happens when p is equal to, say, 0. Again, we're just trying out different values of p to see if we can make or try to come up with any ideas on why this behavior would make it diverge. So if p is equal to 0, the series we actually get is 1 over n to the 0, which will just be 1 over 1. In other words, this is the infinite series of when we're adding 1 forever. And as we discussed before, this series is divergent. The sum is going to add towards infinity. Okay, so far we have two values of p out of the infinite possibilities. Let's try what happens when p is equal to negative 1. So when p is equal to negative 1, we have this as a series of 1 over n to the negative 1, which using the powers of, or the rules for powers, when we have a negative power, that's going to bump something either into the numerator or the denominator. In this case, it's taking the n from the denominator and pushing it into the numerator. So this is actually just the series of n. So this looks like the sum now of 1, plus 2, plus 3, plus 4, and so on. This series is going to diverge. So what it looks like is, well, if any number is less than, or any p-value less than 0, we're going to get this type of behavior where something's going to pop in, where the n to the p is going to pop back into the numerator. All right, well, let's consider the cases when p is actually greater than 1. Well, that's embarrassing. And the way we're going to do this is we're just going to hit our p-series with the integral test. So what our function f of x looks like now for integral test is the function 1 over x to some power p. So let's try to check it out. And again, for the integral test, we want to concern ourselves with three things. We want that function f of x to be positive. We want it to be continuous. And we also want it to be decreasing. And what we see is, well, as long as p is greater than 1, or for that matter, as long as p is greater than 0, this function can be decreasing. You can check it with taking its derivative. But let's go ahead and just perform this improper integral. Again, all three things can be checked, and our function will satisfy these three criteria, but go ahead and do that yourself. So this improper integral, again, from 1 to infinity. For our function now, 1 over x to the p dx. So let's first introduce the limit to take care of that infinite bound. And once we have that limit, let's rewrite the 1 over x to the p as x to the negative power p using algebra. And the reason we can do that is, well, the reason we want to do that is just to simplify the antiderivative, because now we can see we can just use the antiderivative power rule. So the antiderivative, again, will take x to that power, bump up that power plus 1, while we also divide by that power plus 1. And again, we can now evaluate this at 1 and c. So let's plug in these bounds and see what happens. So this is the limit as c goes to infinity. Of negative 1 over p plus 1 times the quantity now of c to the 1 minus p power minus 1 to the 1 minus p power. Okay, now let's think about what this limit can be. C is going to infinity. We're raising c to a power. Well, if c is going to stay in the numerator, this is going to go to infinity. So for example, there's a very big difference whether we do something like limit, say, as c goes to infinity of c squared versus something else like the limit as c goes to infinity of 1 over c squared. Well, the first case, the limit as c goes to infinity of c squared, that is blowing up to infinity. Versus the bottom case, where we have 1 over c squared, this is going to 0, which converges, while the top case diverges. Basically, what we want to make sure is that we are going to be in this bottom case, where everything converges. In order to do that, we need to make sure that the 1 minus p, we need this to be negative to throw that c in the denominator. So let's go ahead and do that now. So, if 1 minus p has to be negative, that means negative p has to be less than negative 1. In other words, p has to be greater than 1 in order to converge. So again, for the p-series, what matters for us, we just went through the p-series and showed what values of p would make this converge. You can do a similar calculation and basically see or convince yourself that, hey, when 1 minus p is greater than or equal to 0, this integral isn't going to converge. But the real important thing for the p-series is remembering this fact. When p is greater than 1, the p-series converges. When p is less than or equal to 1, the series is going to diverge. And the only way that we could show whether or not this p-series converge or diverge was using our friend now, the integral test. So please try to remember this p-series. It's going to be very, very important as we go on with series convergence and divergence tests.